Hey everyone, welcome back to the channel. In this masterclass we are doing a complete, from the ground up deep dive into dependency injection and bean lifecycle. By the end of this video you'll understand it well enough to use it confidently in production and explain it clearly in an interview. If that sounds good, make sure you are subscribed and let's get started. Almost no real object works alone. Every serious Java application is a web of objects that depend on each other, and the decisions you make about how those dependencies are wired together have enormous consequences for testability, maintainability, and correctness. We are going to build a complete mental model of dependency injection from the ground up, then trace exactly how Spring implements it under the hood. Take a concrete example, an order service in an e-commerce system. It cannot do its job without a repository to persist orders, a payment gateway to charge cards, and an email service to send confirmations. These collaborators are its dependencies. The architectural question that unlocks everything is deceptively simple: who creates those dependencies? The answer you give shapes every downstream decision about testing, configuration, and lifecycle management. Quick pause: if this is useful so far, drop a like, subscribe for a new masterclass every week, and share it with a teammate who would find it useful. Now, back to it. This is the day one answer. Let the object create its own dependencies inside the constructor. It compiles, it runs, and it looks perfectly reasonable at first glance. But 2 lines of object construction are hiding 4 serious architectural problems that will cost you dearly as the codebase grows. Each problem compounds the others. The testability issue means every test touches a real database. The tight coupling means changing persistence technology requires opening business logic classes. Scattered configuration makes environment-specific deployments fragile. And without centralized lifecycle management, resource leaks and duplicate instances become runtime surprises rather than compile time catches. Every one of these problems has the same root cause: the object is in charge of something that is not its business. In the self-wiring model, order service reaches outward and constructs its own collaborators. It is both a consumer and a factory. In the dependency injection model, an external IoC container owns the creation and lifecycle of every object. Order service simply declares what it needs, and the container supplies it. Order service is now only responsible for its own business logic, which is exactly the right scope of responsibility. Dependency injection is not a Spring concept, it is a design principle, and Spring is one very powerful implementation of it. The inversion here is subtle but profound. In traditional code, your classes orchestrate everything, calling libraries and creating collaborators. With IoC, the container is in charge of orchestration, and your classes become passive participants that simply declare their needs. That shift is what makes large-scale Java applications manageable. Dependency injection is not just a Spring feature, it is an architectural discipline rooted in a principle called inversion of control. We will cover what the container actually does, the 3 injection mechanisms Spring provides, and build a precise understanding of why constructor injection is the one you should reach for by default. In a traditional object model, your code is the driver. It calls new, wires references, and owns the lifetime of every collaborator. Inversion of control flips that model. You declare what you need, and the container decides how and when to satisfy those needs. Martin Fowler gave this specific pattern its name in a 2004 article that remains essential reading: "The thinking has not aged." Spring exposes the container through 2 key interfaces. Bean Factory is the foundational, lightweight layer. It creates beans lazily, only when requested. Application Context extends Bean Factory and adds AOP integration, event publishing, internationalization, and resource loading. In a Spring Boot application, Spring application.run creates and manages an application context automatically, so you rarely touch it directly, but understanding where it sits in the hierarchy tells you exactly what you are working with. Field injection is the most visually compact form. Annotate a private field with @AutoWired, and Spring uses reflection to inject the value. It requires no constructor, no setter, and looks almost effortlessly clean. That apparent cleanliness is deceptive, and we will unpack the problems it hides in the constructor injection deep dive shortly. Setter injection calls a dedicated mutator method after the object is constructed. This is the right tool for optional dependencies, collaborators the bean can operate without, and for scenarios where a dependency might legitimately be swapped after initial wiring. The core weakness is that a bean can be fully instantiated yet still missing a mandatory collaborator, leaving it in a partially wired, potentially broken state. Constructor injection passes every required dependency at the moment of object creation. The fields can be declared final, guaranteeing immutability. The object simply cannot be instantiated without its dependencies. There is no partially wired state to reason about. Spring has officially recommended this approach since version 4.x, and from Spring 4.3 onward the @AutoWired annotation is entirely optional when a class has exactly one constructor. The choice between injection styles is not stylistic, it carries architectural consequences. Constructor injection makes dependencies explicit, enforces valid object state, and keeps fields immutable. Setter injection has a narrow legitimate use case around optional collaborators. Field injection trades away testability and clarity for visual brevity, which is rarely a worthwhile trade in a production codebase. These distinctions will matter even more as we move into the deep dive. This section is about one of the most consequential decisions you make every time you write a Spring Bean: how you inject dependencies. The choice is not stylistic, it has real implications for immutability, thread safety, testability, and how quickly your application fails when something is wrong. Let's build a concrete mental model. Think of injection style as a contract your class makes with the outside world. Field injection is a passive, implicit contract. Dependencies are invisible from the class signature, and callers have no idea what the object needs to function. Constructor injection is an active, enforced contract. The constructor lists every requirement, and the object simply cannot be created without satisfying them. That difference ripples through immutability, testability, and failure behavior. The fundamental sequence is what separates the two approaches. With field injection, the object is constructed first and dependencies are written into it afterward, which is why the fields cannot be final and why missing dependencies surface at runtime. With constructor injection, all dependencies must be resolved before the constructor is ever called, so the fields can be declared final and any missing bean causes an immediate startup failure. The order of operations is everything. Here is the field injection pattern you will still encounter in legacy codebases. Notice that neither field is final. Spring must write to them after construction, so the compiler won't allow it. There is no way to know from looking at this class signature that it needs a payment gateway or an inventory client. And if either bean is misconfigured, you will not find out until placeorder is called, potentially under production load. Constructor injection transforms the same class. Both fields are now final, assigned exactly once, in the constructor and never again. The constructor signature is the full dependency manifest. Anyone reading or calling this class knows precisely what it needs. Spring resolves both dependencies before the constructor runs, so a missing bean throws a bean creation exception at startup, not a null pointer exception at 2 in the morning. The final keyword is not cosmetic. A final field in Java is written exactly once and can never be reassigned, which means the JVM's memory model gives it visibility guarantees across threads without any additional synchronization. When your bean's dependencies are final, the bean is immutable with respect to those dependencies, and immutable objects are inherently thread-safe. Field injection closes that door by definition. Spring needs mutable fields to perform injection after construction. Failing fast is a core principle of resilient system design. With field injection, a misconfigured or missing bean lets the application start successfully. The problem only appears when that null field is accessed, which could be deep in a business-critical path, under load, at a time when diagnosis is hardest. Constructor injection enforces fail-fast behavior. If any dependency cannot be satisfied, the application refuses to start. Your deployment pipeline catches it, not your users. As a bonus, circular dependencies, which field injection silently permits, are detected and reported at startup too. Most developers use Spring daily without ever seeing the machinery beneath it. We are going to walk through every phase the container executes, from the first class path scan to the final destroy callback. Understanding this sequence is what separates an architect from a framework user. Spring's startup executes 6 ordered phases for every bean. Bean definition registration comes first, nothing is instantiated yet. Then post-processors modify the registry, then the container resolves dependencies recursively, then proxies and interceptors are woven in, then initialization callbacks fire, and finally the live instance lands in the singleton cache. Shutdown mirrors this in reverse. A bean definition is a blueprint, not an instance. It carries the class name, scope, constructor argument types, and lifecycle method names. The container stores every blueprint in a map called bean definition map before a single object is ever constructed. Only when a bean is needed or eagerly initialized at startup does the container use this blueprint to produce a live instance. The container maintains 2 maps in memory simultaneously. The blueprint registry holds every bean definition, keyed by bean name. The singleton cache holds every fully constructed singleton, also keyed by bean name. Between registration and instantiation, bean factory post-processors can mutate entries in the blueprint registry. This is exactly how property placeholder substitution replaces $brace expressions with real values before a single constructor is called. The class that executes this logic inside Spring is Constructor Resolver, located in org.springframework.beans.factory.su port. Step 2 is why a single constructor bean just works without any annotation since Spring 4.3. Step 3 is the most important detail. If a required dependency has not been built yet, the container pauses and builds that dependency first, recursively, before completing the current bean. This is how the entire dependency graph assembles itself bottom-up. Bean post-processors are the extension point responsible for the majority of Spring's declarative features. When you annotate a method with @transactional, no bytecode is rewritten at compile time. Instead, a bean post-processor detects that annotation at startup and wraps the bean in a proxy that intercepts calls. The same mechanism powers Spring security method level annotations and Spring AOP aspects. Your bean class stays untouched, only the reference stored in the singleton cache changes. Once a bean post-processor has had its turn, the initialization callbacks execute in a fixed order at post-construct, then after property asset, then any XML declared init method. This ordering is guaranteed by the container and is important when you mix styles. For example, if a third-party library implements initializing bean while your subclass uses @postconstruct, the @postconstruct runs first. On shutdown, the sequence mirrors startup but runs in reverse bean creation order, so the last bean created is the first to be destroyed. This section covers the real-world constructor injection patterns you will encounter in professional Spring Boot codebases, then moves into 2 advanced topics every senior Java developer must understand: object provider for optional dependencies and circular dependency resolution. The 2 fields are declared final, which is the critical detail here. Final fields give you a compiler-enforced guarantee that order repository and payment gateway can never be null, can never be reassigned after construction, and are safely readable across threads. With a single constructor, Spring 4.3 and later injects it automatically without needing the @autowired annotation. @required args constructor generates a constructor for every final field and every field annotated with lombox @nonnull. The generated bytecode is identical to what you would write by hand, so Spring never knows the difference. This pattern is extremely common in production Spring Boot codebases and dramatically reduces boilerplate without sacrificing any of the safety guarantees that final fields provide. When multiple constructors exist, Spring needs explicit guidance. Placing @autowired on one constructor tells Spring exactly which to use. Without it, Spring falls back to the knower constructor, and if no knower constructor exists, it throws an exception at startup. The package private convenience constructor is purely for tests. It lets a test class instantiate report service with only a data source, without needing a full email service wired up. Object provider, introduced in Spring 4.3, is the correct answer to optional dependencies. Unlike @autowired, required is equal to false, which leaves you with a nullable field injection. Object provider wraps the dependency in a provider abstraction. The bean is resolved lazily only when you call getObject, if available, or stream. The if-available method is particularly elegant. It accepts a callback and executes it only when the bean actually exists, so no null checks are needed anywhere in your code. A circular dependency occurs when bean A requires bean B in its constructor and bean B requires bean A in its constructor. Spring cannot instantiate either bean first because each depends on the other already being fully constructed. The same problem arises in longer chains, where service C depends on serviced depends on service C, and service C depends back on service C. With constructor injection, Spring detects these cycles at startup and fails fast with a bean currently in creation exception. The correct fix for a circular dependency is almost always a design fix, not a Spring workaround. If service A and service B depend on each other, they are sharing a responsibility that belongs in a third, dedicated bean. Extracting that shared logic into a mediator, here an order event publisher, breaks the cycle completely. Both services now depend on the mediator, and neither depends on the other. This improves cohesion and makes each class easier to test in isolation. Constructor injection's fail-fast behavior is one of its greatest strengths. You find the design problem immediately on startup rather than at runtime under load. Using field injection or at lazy to silence the error is a red flag, not a solution. When you encounter a circular dependency, treat it as a signal that your domain boundaries need revisiting. Extracting a shared collaborator or introducing an event-driven decoupling is almost always the right path forward. Let's recap the key takeaways from this masterclass. If this helped you, hit the like button, subscribe for a new deep dive masterclass every week, and forward this to a teammate who would find it useful. Drop your questions in the comments, I read every one. See you in the next one.